Hi, I am Arjun. In this session, we'll see how to solve the derivation for a strain matrix, Jacobian matrix, and stress matrix for a CST element. So, for this, we'll consider a two-dimensional CST element having three nodes. Node 1 having displacements q1, q2, node 2 having displacement q3, q4, node 3 having displacements q5, q6. Let us consider a point P within the element whose coordinates are x, y. Okay, in order to start with, initially I'll consider strain matrix. So now a strain matrix can be written like this. Strain matrix epsilon can be written as, for a two-dimensional element, epsilon x, epsilon y, and gamma xy. So since we know that epsilon x can be written as dou u by dou x, and epsilon y is dou v by dou y, and gamma xy is dou u by dou y plus dou v by dou x. Now let us call this as equation 1. Now this is what we are supposed to find out. We are supposed to find out the strain matrix. Now our intention will be to find out these unknowns dou u by dou x, dou v by dou y, dou u by dou y, and dou v by dou x. We need to find out this unknown matrix. So unknown functions, strain functions. So for this I'll use chain rule. Using chain rule of partial differentiation, and here we'll be using a natural coordinate system. So dou u by dou zeta can be written as dou u by dou x into dou x by dou zeta plus dou u by dou y into dou y by dou zeta. This is with respect to zeta coordinate axis, that is for x, and dou u by dou eta can be written as dou u by dou x into dou x by dou eta plus dou u by dou y into dou y by dou eta. Now we can represent this matrix or these equations in terms of matrix as like this: dou u by dou zeta into dou u by dou eta. So if we observe these two equations, here dou u by dou x is common in this, and dou u by dou y is common in this and this. So we keep dou u by dou x and dou u by dou y outside, and if you take out dou u by dou x in this equation, we will be left out with dou x by dou zeta, and here dou y by dou zeta, and in this equation dou x by dou eta and dou y by dou eta. And now finally we can represent this as, this entire matrix can be called as J matrix. So now dou u by dou zeta into dou u by dou eta can be represented like this. This entire matrix now can be replaced as J matrix, which is called as Jacobian, and dou u by dou x into dou u by dou y. Okay, we can call this as equation 2. Now that J matrix can be written like this: J is equals to dou x by dou zeta, dou x dou y by dou zeta, dou x by dou eta into dou y by dou eta. Now this is a Jacobian matrix, which is it is a scaling matrix which correlates between Cartesian coordinates and natural coordinates with respect to differentials of displacement functions. So now what we have to do is, so we need to consider by using isoparametric representation. So we use isoparametric representation using isoparametric representation. So we write like this: x is equals to n1 x1 plus n2 x2 plus n3 x3. So since it is a CST element, we will have three shape functions n1, n2 and n3. So we know that for a CST element, n1 is zeta, shape function 1, n2 is n2 is eta, so we replace n2 with eta, and n3 is 1 minus zeta minus eta, so into x3. And now we will simplify this, and simplification, x can be written as x1 minus x3 into zeta, so we take common from this and this. Similarly, x2 function will be taken common from this, so x2 minus x3 into eta plus x3. Now if you differentiate this equation, dou x by, with respect to zeta, dou x by dou zeta can be written as x1 minus x3, because differentiation of this function with respect to zeta will be x1 minus x3, and this term will become 0, and this entire function x1 minus x3 can be represented as x13. So negative term will be written later in the second. x13 can be written as x1 minus x3. Similarly, differentiating this equation with respect to eta, dou x by dou eta, now it can be written as x2 minus x3, and this x2 minus x3 can be represented as x23. So similarly, we can write for y function. So we will take y is equals to n1 y1 plus n2 y2 plus n3 y3. So n1 is zeta into y1, n2 is eta into y2, n3 is 1 minus zeta minus eta into y3. So again, if y can be written as y1 minus y3 into zeta plus y2 minus y3 into eta plus y3. Again, differentiating this with respect to zeta first. So y1 minus y3. So again, this can be represented as y13. Now differentiate this equation with respect to eta, y2 minus y3, and it can be represented as y23. And by substituting all these variables, this function into J matrix, now J matrix can be represented like this. So J is equals to dou x by dou zeta, dou y by dou zeta, dou x by dou eta, dou y by dou eta. Now this can be represented like this. Dou x by dou zeta is x13, so x13. Dou y by dou zeta is y13. Dou x by dou eta is x23 and y23. So this is a J matrix by relating this to natural coordinates and local coordinates. And now from equation from equation 2 we can write dou u by dou x to dou u by dou y as J inverse dou u by dou zeta into dou u by dou eta, and we know that J inverse is nothing but adjoint J divided by determinant of J. So directly J inverse now can be represented like 1 over determinant of J into x13 minus y13 minus x23, sorry, this is y23 and x13. Okay, now this will be the J inverse. So therefore this equation now can be written like this: dou u by dou x to dou u by dou y can be written as 1 over determinant of J into y23 minus y13 minus x23 to x13 into dou u by dou zeta to dou u by dou eta. Now this is with respect to u coordinate function, that is x coordinate, and similarly we can take the field displacement functions. Okay, and if we consider field displacement function, so u can be represented like this: n1 q1, so n2 q3 plus n3 q5 with respect to u function. So u can be written as zeta q1 eta q3 1 minus zeta minus eta into q5. Now that is substituting the values of shape functions n1, n2, n3. So if you differentiate this with respect to zeta, dou u by dou zeta will be q1 minus q5, and if you differentiate that function, this equation with respect to eta, so we will have q3 minus q5. So the previous matrix now can be represented like this: dou u by dou x and dou u by dou y now can be represented as 1 over determinant of J y23 minus y13 minus x23 x13 to q1 minus q5 q3 minus q5. So in the similar fashion, now we can write for v function, that is displacement along y. So dv by dx to dv by dy can be represented as 1 over determinant of J. So this J matrix remains same: y23 minus y13 minus x23 x13, and so for this q2 minus q6 and q4 minus q6. Okay, now let us consider the strain equation. We know that epsilon x is equals to dou u by dou x. So this is epsilon x, dou u by dou x is epsilon x, so 1 over determinant of J. Now we will write that term: 1 over determinant of J into, so y23 into q1 minus q5 minus y13 into q3 minus q5. So we will do a matrix multiplication: y23 into q1 minus q5 plus minus y13 into q3 minus q5, y13 into q3 minus q5. On simplification, okay, we'll get 1 over j into, so if we simplify, so I'll show the simplification for one term. So y23 q1, so we, as far as possible, try to avoid negative signs. So y23 minus y23 into q5, instead of writing minus y23, so I will rewrite this as y32 q5, so minus into minus, it will become plus, again here also plus y13 q3, so it will become y31 q1, sorry q3, so plus y13 q5. So now this y32, so we have two q5 terms here. So we know that y32 is nothing but y3 minus y2, and y13 is nothing but y1 minus y3. So plus y3 minus y3 will be cancelled, so we will be left out with y1 minus y2, so that y1 minus y2 can be represented as y12. So on simplification, we can represent this as 1 over determinant of j into y23 q1 plus y31 q3. Now this simplification I told, y32 can be written as y3 minus y2, y13 can be written as y1 minus y3, plus y3 minus y3 will be cancelled, so we'll have y1 minus y2, so that can be written as y12, so y12 q5. This is epsilon x. Now similarly we have to write for epsilon y, which is dou v by dou y. So now we can write this as 1 over determinant of j minus x23, so dou v by dou y minus x23. So this is a function what we have to take, minus x23 q2 minus q6 plus x13 q4 minus q6. That is what I am going to write now, minus x23 q2 minus q6 plus x13 q4 minus q6. Now on simplification, now I will write the final equation for epsilon y, 1 over determinant of j. So we will be getting x32 q2 plus x13 q4, so x21 q6. So as far as possible, try to maintain positive signs. So now, so let us write the same for gamma xy. So gamma xy is equals to dou u by dou y plus dou v by dou x. Now we have to write two functions similarly using the matrix. So I will write directly, which is 1 over determinant of j minus x23 q1 minus q5 plus x13 q3 minus q5 plus y23 q2 minus q6 plus minus y13 q4 minus q6. Upon simplification, now I will write the final equation for this, 1 over determinant of j, so x32 q1 plus y23 q2 plus x13 q3 plus y31 q4 plus x21 q5 plus y12 q6. Now finally writing into strain matrix. So epsilon is equals to epsilon x, epsilon y, gamma xy. So now 1 over determinant of j is common, so we'll have to write the equations. So now this is gamma xy and we have 6 nodal displacements. So we'll write coefficients q1, q2, q3, q4, q5, q6, and the coefficient of q1 in epsilon x equation is y23, coefficient of q2 is 0, coefficient of q3 is y31, coefficient of q4 is 0, q5 is y12, and q6 is 0. Similarly, in epsilon y equation, coefficient of q1 is 0 and q3 is x32, q3 is 0, q4 is x13, and q5 is 0, q6 is x21. So gamma xy, coefficient of q1 is x32 and coefficient of q2 is y23 and coefficient of q3 is x13, q4 is y31, q5 is x21 and q6 is y12. Now this entire matrix is a B matrix, this entire matrix is Q matrix, and this is a strain matrix. So now this is epsilon is equals to B into Q. This is a strain matrix. And if you want to find out stress matrix, so we write sigma is equals to D into B into Q, and for plane stress condition, D matrix can be written like this: E divided by 1 minus mu square, 1 mu 0, mu 1 0, 0 0, 1 minus mu divided by 2, and so finally the stress matrix can be represented like this: sigma is equals to D is E divided by 1 minus mu square, 1 mu 0, mu 1 0, 0 0, 1 minus mu divided by 2 into B matrix, B into Q. So B matrix is 1 over determinant of J, y23 0, y31 0, y12 0, 0 x32, 0 x13, 0 x21. Now x32, y23, x13, y31, x21 and y12 into all the nodal displacements q1, q2, q3, q4, q5, q6. This is a stress matrix. This is a stress matrix. If you have any clarification, please contact me on this number, or you can mail me on the following email ID. Thank you.